Okay, so we are talking about the regular language, regular set. So, today we will discuss the necessary property of a regular language. Suppose a language is regular, then we have this property which is called pumping lemma, and this is very powerful tool to test whether a language is I mean if it is not regular. I mean if it is failed the pumping lemma, then we can straight away say the language is not regular, because if it is regular, then the pumping lemma will be will hold. So, what is pumping lemma? So, this is for a regular set or regular language. So, again what is the regular set? Regular set is, suppose we have a, this is the set of finite alphabet, this is alphabet set, it could be 0 1, it could be a b, anything. I mean this is the alphabet set, and we have a L which is a subset of sigma star. Sigma star means it includes the epsilon also. Now, this is called language, any subset of sigma star is called language, and when we say this language is regular or regular set, if there is a automata which is accepting this, that means if every string of this language, every member of this language, every string belongs to this language is accepted by that automata. So, this is a regular set if there exists a DFA, if there exists a DFA M with the same set sigma delta q 0 f such that the language of this DFA is same as language of L. That means, every string of this set must be an accepted string of this DFA. Okay. So, that means every so given this, I mean we must have this DFA with the q is the finite number of states, and this is the sigma, this is the delta tangential rule, and q 0 is the starting state and f is the final state. So, L will be regular if the language of this DFA is same as language of L. So, that means, if x belongs to L, then delta hat of q 0 x, this must belongs to f. Okay. So, every string of L is accepted by this DFA. So, that is the regular language. Okay. Suppose we have a regular language. So, then we will have a necessary condition for a regular language, that is called pumping lemma. So, suppose L is regular, let L, which is coming from sigma star, be a regular set or regular language. Then this imply what? This imply we have a DFA, there exists a DFA which is accepting this, say q 0 f, which accept this such that the language of this DFA is same as language of L. Language of DFA is nothing but this is the set of all string which is accepted by this DFA. We start with q 0, with this x we must reach to one of the final state. So, we are at q 0, with the x we must reach to a one of this final state. It may have one or more final states. Okay. So, this is the, now this is a DFA. So, it has a finite number of states, q is finite. So, suppose q is n, say let n is the total number of states. So, we just denote q by say q1 q2 like this. So, we will just denote this by so q0 q1 qi, these are the no not qi. So, these are the states, say q n minus 1 if we have n number of states. Okay. And some few states are the final state, at least one, and this is the starting state. Okay. Now, we will consider a string of length more than n. We consider a string from this of length more than n. Say we write this x as a1, a2, am, where ai's are coming from sigma and m is greater than n or greater than equal to n. So, this we write as z. We follow the same notation in the class note. Okay. So, let us consider a string of length more than n. N we know, n is the number of states more than n, and that is the string. Say if it is strictly greater than, then we have this strictly, otherwise we can have greater than equal to. Okay. So, now we will read the string. So, we start with del q0. Suppose with a we go to q1. So, this is with a1, and with a2 we go to again q2 like this. With a3, this is we are not, I mean this is some names ordering of some states. Okay. So, with q2 we go to q3 like this, dot dot dot, say suppose with ai we go to qi. Okay. So, that means delta hat of q0 a1 a2 ai. So, this is the substring a1 a2 ai is basically qi, say this is a, it has to reach to a state which is qi. Okay. Now, so we are at qi. So, if we continue this, so then up to this we will be at say qm, after this am. Okay. Now, we have only how many states? We have only n number of states. Since we have n number of states and here m is greater than n or greater than equal to n, then some of the then all the qi's cannot be distinct. If all the qi's are distinct, then we have how many states? We have total m plus 1 state, which is more than n, plus 1. Okay. So, that is not possible. So, all the states over here cannot be distinct. So, that is one observation. All qi's are not distinct. So, that means some of the qi's has to be repeat, because we do not have that many states, we have total n number of states, and here we have m plus 1 which is greater than n. So, that means some of the qi's has to be repeated. So, that means what? That means we should have a state over here, that means there exists a I and k which is less than n, such that qi qj will be qk. Okay. Qj will be qk. So, that means after this, say let me draw it again. So, we are going like this q 0 a 1 will go to q 1 dot dot dot, say we are q j with a j. Now, suppose up to q j it is okay, all are distinct. Now, then q j plus 1, then up to q k, this q k must be same as q j, then this is a k dot dot dot, then this is q m a m. So, this will be the situation. So, this state and this state has to be same, because we have only n number of states. So, there will be in the middle, there will be two states which will be same, and that two state has to be number from 1 to 0 to n. Okay. And j must be less than k. So, this is the observation. So, these two states has to be same. So, that means after q j it will again come back by the string of a j plus 1 like this. So, if you write this, this is similar to, so q 1. So, we go like this. So, we reach to the state q j which is same as q k, and this is the string of a 1 a 2 up to a j, all are over distinct over here. Then it has to repeat. So, this repetition, this is reading the string of what? A j plus 1, a j plus 2 up to a k. This is repeating, and then we have a k plus 1 to a m, and then we are reaching to q m. Okay. So, this is the situation, this is equivalent to this. This is the starting state. So, if we have a string of length more than n, that is say a 1 a 2 a m, then we must have this situation. What is the situation? Then we must have this string, I mean these two states in the middle which will be same. That means, in that path we have a repetition. So, we denote this by let us use some symbol, say this is u and this is v and this is w. So, this is our z. So, z will be written as u v w, where length of u v is less than n and length of v, this is v, length of v must be greater than 1, because length of v is nothing but this is our v. So, let me write it again. So, z will be written as a 1 a 2 up to a j. So, that is this u, and then a j plus 1 to a k. This length is k minus 1, this is our u v and a k plus 1 to a m, and this is our w. Okay. So, this is length of, so now length of this, because I j are coming, I j are less than k and I is less than, sorry, I j k, sorry j k, j and k are less than n and j is less than k. So, from here we can write u v, length of u v is k, which is less than n or less than equal to n, and length of v is k minus j, which is greater than equal to 1. So, this is the thing, and with u we are going to this state q I, q j, which is same as q k, and there we read a string, again we come back to here. So, there are some repetition of the state, there may be some other states which is also repeating, which are may be distinct. So, this will again come back here, but at least this is the first state which is equal to the which will be repeating, because it has to be there, because otherwise we have only n number of states, and if we need to have all distinct states, then we need total m number of states, and sorry m plus 1, which is greater than n, strictly greater than n, because n is greater than equal to n. So, m plus 1 is greater than equal to n plus 1. So, that is not possible. So, that is why it is there. Okay. So, this is the observation. So, let me refresh this. So, this we will write in a theorem form, that this is basically called pumping lemma. I mean, we have to write in a theorem form. So, what we have? So, we have given a string which is more than this, then there exists a j and k which is less than n, such that z will be written as u v w, where u is a1 a2 up to aj, v is aj plus 1 to ak, and w is ak plus 1 to am. u v w. Okay. Now, such that this u v, which is of length k, which is less than n, because k has to be less than n, and the length of v, which is nothing but k minus j, which is also greater than 1, greater than equal to 1. Now, if q m, so it is ultimately going to the q m. We are starting with q 0, we are reading this u, and we are going to q j, which is same as q k, and then with this v, we are again come back to this, and then with w we are going to q m. Now, if z is a final, z is a accepting string, that means this if q m belongs to f, if q m is a final state of the automata, then z is an accepting string. Accepting string. Okay. So, if you take z from the L, which is a regular language, then every string of L has to be accepted by this automata. So, that means, if z is like this, then q m has to be an final state. Now, from here we will draw some observation. So, q m is final state means, so this is delta z of q 0 with z, z is u v w, this is nothing but q m. Okay. Now, from here we can have some observation. Yeah, so okay, can you write this? So, we know z is a a k plus 1 am, z is a acceptance string, and which is written as, this is u, this is v, this is w, and we know that from q 0 with u we are going to some state q j, and with v we are coming to same state, that is q k, which is same as q j. So, this is with V, we are coming to same state, and then with W we are again going to Qm. Now, if we discard this string, then also we are reaching to the final state with the starting state, because if we just have a string that u and v, u and w, sorry, then also delta hat of, what is delta hat of q 0 u and w? It is also Qm, because we are by u, we are, because this is same as, okay, this is same as delta hat of q 0 u, then we can read w. This is the way, this is easy, can be easily proved. This is the recursive definition of delta hat. This is the way how we read delta hat. So, this is nothing but delta hat of, so where is q 0 u? We are going to, which is same as q k w. Now, from q k w we are reaching to q m with the by reading the string w. So, we can just omit this v, still we are reaching to the final state. This is one observation. Even we can repeat that v. So, how to do that? So, if this is L, then we have observed u w is also belongs to L. Not only that, u v to the power I w, v to the power I means I is greater than equal to 0. If I is 0, then v is not there. If I is 0, then it is u v, and just now we have seen u v is belongs to L. Now, if I is 1, then this is u v w, this is nothing but z, this is belongs to L. Now, if I is 2, then u v square w. Now, how this is be this will be again reach to the Qm, because, so to read this, what we do? We start with q 0 with u, we go to q j. Now, with v we go here, again with same v we hop here, pumping, we are pumping this state. So, 2 times we will do that, and we will, then after that we read w, this is 2 times, this is v square, we reach to the Qm. So, that means delta hat of q 0 u v square w is also Qm. So, not only v square, any I, delta hat of q 0 u v to the power I w is Qm. This is nothing but called pumping lemma. We can pump, there is a substring v which we can pump there, we can hop there. So, let us write it in a formal way. So, this is nothing but pumping, and this is the necessary condition. If our language is regular, then it should have this property. If our language is regular, then we should have a n, n is nothing but the number of states for that automata, and if we take a string more than n, then in that string there is a substring which we can reuse it, we can pump there to get a bigger string, and still we that should also belongs to L. So, this is the necessary condition. Let us write this lemma. This is the formal way. Let L be a regular set, then there is a constant n such that this constant is nothing but the number of state for that DFA, which we have seen just now, such that if z is any string any string or word in L, and if length of this is more than n, we may write. So, there has to be some UVW in such a way that u and v length is less than n and length of v must be greater than 1. There has to be such string, and for every I greater than or equal to 0, this u v to the power I w must belongs to L, and this must be true for all I. So, this is called pumping lemma. Okay, this is the statement of the pumping lemma. So, what it is telling? It is telling that if we have a regular set L, then we must have a constant n, that is nothing but the number of states in the DFA. Anyway, we must have a constant n such that if you take a string from this L whose length is more than n, then we must able to write this in terms of UVW, these are all substring, such that the length of this substring UV is less than n, and this substring has to be greater than 1, and we can just this is called pumping. We take u, because if I is 0, then this is nothing but this. If I is 1, this is UVW. If I is 2, UV square W. If I is 3, UVQW, like this. So, all must belongs to n. This is the necessary condition. If this is regular, then we have this, but this is not sufficient. If this condition satisfied, we cannot say that a language is regular. So, if a language is regular, then it must have this property. So, to check a language is non-regular, this property is very much useful, this lemma. So, that we will discuss in the next class. We will take some example, and there we will prove that this language are non-regular, which is because of failing this pumping lemma. We will talk about it in the next class. Thank you.